I'd just like to start by thanking the organisers for giving me the opportunity to speak today. And I'm going to be talking about basically what constraints that star-forming environments can place on the formation of the solar system, what the solar system looked like when it was forming, the environment it formed in, and how this can help us find solar siblings and stuff. So I'm trying to relate star formation all the way back down to looking for something that is like the Earth and our solar system planetary, our planetary system. So just a bit about star formation, planet formation, sorry. You've seen this picture already several times today. It's one of our favorites. As Lucas was saying in the previous talk, planet formation seems to occur very early on in the lifetime of protoplanetary disks, very quickly. And so planets and stars form at the same time. They form simultaneously. And so anything that is happening to your star is likely to be happening to your planets while they're forming as well. So it seems like planet formation and star formation are actually much more linked than we've previously thought. And what can looking at the solar system today tell us about what was happening to our planetary system while it was forming? So as has previously been said, we have 8 planets in our solar system and lots of dwarf planets. There's always more being found. And all of these seem to have approximately spherical orbits and are nicely aligned. The Kuiper Belt objects seem mainly undisturbed. However, there are 1 or 2 that are kind of a bit quirky, like Sedna. And the only thing that we can really think about that describes Sedna's orbit is something like either it was a captured object or a stellar interaction actually disrupted its orbit and did something weird. So that's telling us that the sun was, when it was forming, in the presence of other stars. The other big one that I'm going to be talking about today is the presence of these things called SLRs. So what are these SLRs and why are they important? I'm particularly focusing on aluminium-26 and iron-60. These have very short lifetimes, and they are detected in carbonaceous chondrites, which we think are things that represent the initial conditions when planets were forming. So the fact that they are in these chondrites means that these short-lived radioactive isotopes had to be present at the very beginning of planet formation. And we actually think they're quite important to forming something like planet Earth. So I have to warn you, I am an astrophysicist, not a geophysicist, so apologies if I get this a bit wrong. But aluminium-26 and iron-60, we think, are some of the primary heating sources for forming planetesimals, which are the building blocks for planets. Aluminium-26 seems important for core separation, and for creating an iron core and having this molten core on planet Earth. And as we know, the molten core is responsible for things like magnetic fields on planet Earth, which protect our atmosphere from solar radiation. And they're also responsible for possibly things like plate tectonics, which has been previously said is connected to the carbon cycle on Earth, carbon cycle on Earth, which seems really important for life, possibly. So all of these things is quite interesting, but how do we get these radioactive isotopes? They're actually very hard to create, and this is where the kind of interesting stuff with the birth environment of the solar system comes from. We can make aluminium-26 in cosmic ray spallation, but it's not very effective, and you can't make iron-60. So we don't think that's a method for enriching the solar system. You can form them in things called asymptotic giant branch stars, but these are old stars, and we're looking at young star-forming regions when everything's just starting to kick off, so it's highly unlikely that it's going to be from this. So there's kind of 2 methods that people think that you can actually get these isotopes. One of them is forming from material that already has it in it. But as I said before, they have really short lifetimes, and so if you form in pre-enriched material, the funky stuff you have to do with star formation to get that, we can't see observational evidence of forming, like you have to have strange things going on with star formation, and we can't really make it happen in simulations, so we think that this is not the way. So the best method, we think, is to get direct enrichment from a supernova explosion, which is a massive star that creates these isotopes when it goes bang, and the supernova ejector directly accretes onto the protoplanetary disk, enriching your system. But this requires the presence of a massive star, and massive stars in comparison to something like the Sun are really rare. And you mostly find them in high-mass clusters, which brings us round to star formation. Stars don't form in isolation, they usually form in groups called clusters, and these clusters range in size from about tens of stars to millions. You're much more likely to form a few stars than forming these massive clusters. But as I said before, massive stars are really rare, so we see them usually in these high-mass, big clusters. The densities of these star-forming regions also is roughly about, we think, 100 solar masses per cubic parsec we've seen from observations. These densities in your star-forming environments can affect protoplanetary disks, depending on how dense things are. And I'll talk about now the effects of what your cluster can do to your star formation. So there's something called photoevaporation of protoplanetary disks that Pierre talked about briefly. So this is where you've got massive stars in your cluster, and they can actually blow away the material of your protoplanetary disk and destroy it completely, possibly within a few million years, some new research is showing. So if you look here, these highlighted boxes are showing you what we think are protoplanetary disks, and you can see that they're actually like material we think is being completely blown away from them. And these are in high mass clusters with massive stars. So that's bad news because you might actually stop planet formation happening. There's also stellar encounters and interactions. I mentioned that Sedna's orbit is a bit odd. So stellar interactions can do some really bad things to your planetary systems in dense environments. So this is a simulation that Parker and Quans did, where they put a planet at about 30 AU, so about Neptune's orbit, I think. And it had a circular orbit, and then they put these planets and stars in a dense cluster and saw what happened literally just by having interactions between stars. And after 10 million years, this is what happens to your planets. So you can see that your planet's eccentricity can massively increase. You can also change the radius a lot, and these red crosses are showing you planets which have been captured from other stars onto completely captured from other stars. So you can massively disrupt planetary systems, and this is going to be bad news if you're trying to create a stable system. So dense stellar environments seem very hostile to forming something like the solar system. However, it has been previously thought that the Sun was going to form in a high-mass cluster because of this need for a massive star. Lots of simulations and previous studies have looked at high-mass clusters and have been focusing on them, but as I've said before, stellar interactions and photoevaporation can do really bad things to your planetary disk. So the probability of forming something like the solar system in a massive cluster is very, very low. I'll tell you the percentages later, but it's like 0.1 to 0.6 of planetary systems in these kind of high mass clusters can actually survive and end up looking like our solar system. People thought that you needed to have these high mass clusters because of the necessity of a high mass star, and they thought there was some fundamental relationship between the most massive star you can get in a cluster and the mass of your cluster. And this red line was showing you what the studies were saying. However, you can see these points here. These are observational points which show you that clusters with massive stars, but these clusters only have masses of about 10 to 100 solar masses, but they have these massive stars in, which will go supernova. So what we wanted to do is look at these low mass clusters, which potentially don't have these hostile effects, and see whether actually we could create something like a solar system by running n-body simulations. So the first thing first was to see how many of these clusters we get, whether these are actually viable environments. We see some observational counterparts, but how many do we actually think we could get? So what we did was we looked at the clusters that we see in the galaxy, and this is the purple line. So you can see that for low mass clusters, so something that's got like 100 solar masses in it, there's a huge amount in comparison to something that has like hundreds of thousands of solar masses. What we did was we randomly populated these clusters with stars from the IMF, which is just describing the probability of forming a star, forming a mass of a star. And the important one to look at here is this blue line. This blue line is telling you clusters that contain one massive star that will go supernova quickly enough to enrich your planetary system with these elements. And you can see that actually 10% of the population of low mass clusters from our simulations have one massive star in. which is great news for us because this means that these are probably better environments for forming something. However, we then had to run n-body simulations to see how efficient they were at actually enriching stuff. So we ran the clusters and we ran the simulations, and we found that something that is like our solar system, so it's enriched with these materials, it's unperturbed and is has a G-dwarf star, is very, very, very low. And I think that actually this poses quite an interesting question to this community. It's 0.1 to 0.6 of our stars actually end up looking like something like the solar system. This is probably an underestimate. There's new work going on by geophysicists who think that we're better at capturing these elements than we previously thought, but this number doesn't change that much. However, the good news is that our low-mass clusters were as efficient at producing these things as the high-mass clusters. So against the bad news, it means that we are finding probably more of these things than we previously thought. So just in summary, star-forming environments do affect planet formation and can do some really nasty things to your planetary systems. If you're wanting to create something that's very stable and looks like our solar system, which, as has been previously said, is our only example of life at the moment, you do need to take into consideration what is happening to your planets while they are forming. Aluminium-26 and iron-60 seem very important for creating something like planet Earth for this molten core. The enrichment of these materials is probably most likely through supernova explosions, which are very rare. So this poses a very interesting question of how likely is it that we're actually going to get something looking like the solar system. Low-mass clusters are possibly better environments for forming something like the solar system than high-mass clusters, which was previously thought. And this is good news, because this means that this has reduced the constraints on the formation of the solar system, and it means that there's a higher probability of us having stuff like us out there. So thank you very much.